Good morning, students. This is Anjali, Assistant Professor, Department of CSE, AIML, IARE, Hyderabad. Students, we have learned in last class some bias theorem and conditional probability. So first, moving towards our main topic, first we will see that what we have learned in the last class. In last class, we have seen that bias theorem and conditional probability. Conditional probability. These both theorems, both terms are related with each other. Actually, we can say that this bias theorem is totally dependent on the conditional probability. What is meant by conditional probability? That conditional probability means if you want to find out any possibilities of any event, so at that time you will apply some conditions, so that is the conditional probability. Just for example, P of A given B is equal to P of A intersection B divided by P of B. That means this is your conditional probability. P of A, you have to find out P of A, but B already occurred. Then after that, you have to find out the probability of both A and B, and then divided by probability of B occurring. This is your conditional probability. Then what is the bias theorem? Then bias theorem also we can say that P of A, probability of A given B is equal to probability of B given A into probability of A divided by probability of B. This is your bias theorem. That means this bias theorem will contain some posterior, some prior hypothesis, some evidence. All these things will be available in the bias theorem. That means here A is your hypothesis. A is your hypothesis. Then B is your evidence. Then this is your prior. So this is all about, we have seen that bias theorem and conditional probability in the last class. Now we will see that, we will learn that collectively exhaustive event. Now this contains are collectively exhaustive events, random variable, probability distribution for random variables, and spatial probability distributions. Now we will see one by one. First, collectively exhaustive events. Generally, when given a set of two or more events, if at least one of the events must occur, then such a set of events is said to be collectively exhaustive. That means, for example, we can say that if you have a set of two or more events, and from them at least one event occur, so at that time we can say that it is your collectively exhaustive. Here there is one example. I have taken the set of events, temperature less than 60 and temperature greater than 90. That means these events are not any collectively exhaustive, because there is another third option also. So this is not your collectively exhaustive event, because there are two conditions: temperature is less than 60 and temperature greater than 60. But what about the middle term? That means temperature should be middle bit, or we can say temperature should be between 60 and 90. So definitely there is third condition is also occurring. So we can't say that temperature less than 60 and temperature greater than 90 is a collectively exhaustive. But they are mutual exhaustive because they cannot happen at the same time. What we are saying that our whatever we have declared temperature, our temperature is not collectively exhaustive, but it is mutually exhaustive. Why? Because it is not happening, or it is not happening at the same time. So again we can say that, again we can take another example. In the dice roll, set of events of rolling 1, 2, 3, 4, 5, 6. You know that if we have rolled any dice, its a sample space will be 6. That means it will contain 6 value, 1, 2, 3, 4, 5, 6. Not more than 6 and not less than 1 also. So it will contain only 6 values. And these values are collectively exhaustive because these are the only possible events, and at least one of them must happen. That means we can say these are collectively events because we know that from only these events we will get at least one output. Rather than instead of these values we will not get any output, but we will get the output only from these values. So this is your collectively exhaustive event. Now we can see that here this is table, just it's containing the rolling dice numbers 1, 2, 3, 4, 5, 6, and these all values are collectively exhaustive. Even we can take another example, flipping a coin. Suppose we flip a coin one time. We know that the coin must land on one of the following values. And we know that the coin has only two values, coin has only two sides, so it will occur only two events, either heads or either tail. And the set of events, head or tails, would be collectively exhaustive. The second example is that basketball players, we can take a basketball players as an example. Suppose we have done a survey and they are asking individuals to select their basketball player position. So there are different responses. For example, point guard, shooting guard, small forward, power forward, and center. These are the possible events. So set of events are point guard, shooting guard, small forward, power forward, and center. And that means these all events are collectively exhaustive. However, the set of events like point guard, shooting guard, or small guard would not be collectively exhaustive because it does not contain all possible outcomes. These are all possible outcomes. That means all these things are the collectively exhaustive. But if we have taken only 3 in the set, that means these are not collectively exhaustive because there are another two chances to get another 2 values. That's why that are not the collectively exhaustive. But when we are keeping all these value in one set, like point guard, shooting guard, small forward, power forward, and center, all these are your collectively exhaustive set. Now, exhaustive events in probability with the example. For example, first example is that in an experiment, 3 coins are tossed at the same time. Consider the following events. No tail appears, B showing exactly 1 tail appears, C showing at least 2 tail appears. That means there are 3 events, and on that basis you have to find out that do they form a set of exhaustive events. There are 3 coins After tossing coin, there are some events that these same events are occurring. A is showing no tail appears, B is showing exactly one tail appears, and C showing at least two tail appears. And after that, you have to find out, are these all exhaustive events? And now we will see that how we will get the exhaustive events, or is it exhaustive events or not. In experiment, tossing a coin 3 times, or we can say that 3 coins tossed at the same time. That means outcome will be same. That means simple sample constitutes the same outcomes in both cases. That means we will get the sample space as a, we can say that n of s we will get 8. And we know that the 8 events, what are the 8 events? We know that all 3 coins will contain head, head, tail, head, then tail, head, tail, then tail, head, and all 3 tails. So these are our possible values. But as per given, first event A is containing no tail appears. No tail appears means without tail, that means all coins are appearing with the head. So we can say that our A event is triple H. That means all 3 coins are containing head. Now, second one is exactly one tail appears. Second one is asking that exactly one tail appears, you have to find out. Now, exactly one tail means this is your second event, this is your third event. That's it. That means there are 3 events we got with the exactly one tail appears. Now then C is at least 2 tails appear. At least 2 tails. At least means minimum 2 tails and maximum 3 tails we can get. So minimum 2 tails. So this is our possibilities: head, tail, head, tail, head, and 3 coins will contain tail. That means there are 4 possibilities. These are our at least 2 tails appear event. Now what we have to find out, we have to check that are they forming a set of exhaustive events? Let's check. And for this purpose, you have to do operation on the 3 events A, B, C, and you have to use union operation. That means you have to apply the union operation on 3 events event A, event B, and event C. Now, on this basis, you have to find out. We know that in A event we got H. Now again we have to find out for B. Now we got H tail, head, tail, head, tail, head, then tail, head. Then again you have to use the union function. Now we got the 4 elements: head, tail, head, tail, head, and 3 times tail. Now we will do union, and after doing union, you will see that all these are containing in the sample space. Just observe it. You can find out these things are available with your sample space. So this is your equal to S. So after solving this problem, we can consider that we can conclude that A, B, and C events are exhaustive events. Now we will find out the another example. Consider the set of first 10 natural numbers. Now check if the following defined events are exhaustive. First event is selecting a prime number. Second event is selecting a multiple of 2. And C event is a choosing a perfect square number. That means you have to take set of the 10 natural numbers. We can say that S is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are our natural numbers. Now we have to find out set A, event A. That means A, selecting a prime number. Selecting a prime number means 2, 3, 5, 7. These are your prime numbers. Now, B event. B event is asking multiple of 2. Multiple of 2, then 2, 4, 6, 8 and 10. And then choosing a perfect square. C event, choosing a perfect square. That means 1, 4, 9. Now you got the 3 events. So after solving this, you have to do union of A, B, C event. And now you will get all the values equal to your S. That means we can say that your A, B, C events are exhaustive events. Now we will see random variable. A random variable is rule that assign a numerical value to each outcome in a sample space. That means we can say that random variable is a rule where we can assign some numerical value for our sample space, and it is a variable whose value is unknown or a function that assign value to each of an experiment's outcome. That means whatever variable we will use, that variable is unknown for us, and that unknown variable we will assign as a experiment's outcome. The random variable can be either discrete or continuous. But when we will talk about the discrete, that means that discrete having some specific values, and when we will talk about the continuous, that continuous will continuous value have some continuous range. And the use of a random variable is most common in probability and statistics, where they are used to quantify outcomes of the random occurrences. So, these random variable generally we are using in the probability and the statistic for quantifying your outcome, for identifying your outcomes of the random occurrences. And now the risk analysts use mostly random variable for estimating the probability of the adverse event occurring. Now random variable is said to be discrete, but when if it assume only specified values in the interval. Your random variable is a discrete only if it is specified in particular interval, otherwise it will be continuous. Generally, we denote the random variable with the capital letters such as X and another is Y. And when X takes the values 1, 2, 3 and so on, it is said to have a discrete random variable. But as a function, random variable is needed to be measured, which allows the probability to be assigned to set of the potential values. Here there is a need to be assigned a random variable for potential values, and it is obviously that your result will be depends on some physical variables which are not predictable. That means your result is totally depend on the physical variable which we are not predicting. Now, see, when we toss a fair coin, the final result of happening to be heads or tails will depend on possibly some physical condition. Generally, we know that the probability is totally depends on some conditions, and sometimes we can't predict some outcome also. Though there are other possibilities or probabilities like coin could break or could be lost also, such consideration should be avoided. And a domain of random variable generally is your sample space, and which is represented the collection of possible outcomes of random variable. Now, understanding a random variable. Actually, in probability and in statistics, random variables are used to quantify the outcomes of the random occurrence. And therefore, we can take just so many values. And random variables are required to be measurable and are typically real numbers. Just we will take the example, the letter X may be designated to represent the sum of resulting numbers after 3 dice rule. Just we will take X could be 3 or X could be 18. How we can consider this thing? Just we can take, we know that the when we will roll the dice, so at that time we will get the n of s 6. N of s 6. And in n of s, there are 1 to 6 numbers. 1 is your lowest number and 6 is your highest number. That means we are rolling a dice or 3 times. So 1 will come 3 times and 6 will come 3 times. So your lower number, when we will add this thing, 1 plus 1 plus 1 plus 1 plus 1, that means 3, and 6 plus 3, 6 plus 6, that means 18. That means your highest value is 3, lowest value is 3 and highest value is 18. Now, a random variable is different from algebraic variable. And variable is an algebraic equation. Generally, it is a known value where we can be calculated. We can take as an equation 10 plus x is equal to 3. Now, definitely you can find out the value of the x, and we will get the x is equal to 7. That means we can find out easily. We can find out easily in the algebraic equation. But on the other hand, random variable has a set of values, and any of those values could be resulting outcome as seen in example of the dice above. Now there are different types of random variable. A random variable has probability distribution that represent the likelihood that any of possible value could be occur. That means random variables will contain some probability distribution which is containing the likelihood, and it is totally depends on what values are occurring. Just let's say that the random variable z is the top face of the die when it is rolled once. But there are some possible values for the z. We can say that 1, 2, 3, 4, 5, 6 are the possible values for the z. But the probability of each of these value is 1 by 6. And they are all equally likely to the value of z. So for instance, the probability of getting 3, or we can say probability of z is equal to 3, when die is thrown, it will be 1 by 6. Definitely we will get the value from the sample space, and so the probability of having a 4 or 2 or any other number on all 6 faces of a die, we will get the same probability 1 by 6. Now, the random variable can be either discrete or the continuous. First, we will see discrete random variable. And these discrete random variable take a countable number of distinct values. Consider an experiment where a coin is tossed 3 times. If x represents the number of times that the coin comes up heads, then x is a random variable that can only have the values 0, 1, 2, 3. That means from no heads in 3 successive coin tosses to all heads. So we can say that X represents the number of times the coin comes up heads. And definitely there are only some possibilities. Either we will get one time, two time, three time, or we will not get the head also. So there are these possibilities. And definitely no other value is possible for the X. Now, continuous random variable. What is meant by continuous random variable? And continuous random variable generally will represent any value within the range or interval. Any value within the range or interval and can take an infinite number of possible values in the continuous random variable. Just we can take the example of some random variable and it involves the measuring amount of rainfall in a city over a year, or you have to find out the average height of random group of 25 people. So drawing a letter, if y represent random variable for the average height of random group of 25 people, so you will find out resulting outcome is continuous figure and height may be change, maybe 5 feet or 5.01. That means you can say that your output is continuously changing and it is continuously changing, varying according to the conditions. And clearly there is an infinite number of possible values for the height. So we can't say that only this height will be available for only every person. So that outcome is continuously changing. A typical example of random variable is outcome of coin toss. Consider probability distribution, in which outcomes of random event are not equally likely to happen. Just if a random variable y is a number of heads and we get from the tossing of two coins, that means y could be 0, 1 or 2. And this means that we can say that there is no any head, there is one head, or we got the two heads on the two coins. Now, however, the two coins land in 4 different ways. Either tail, head tail head, or we can say head. Therefore, the probability of y is equal to 0 is 1 by 4. Since we have one chance to getting no head. Similarly, probability of getting a 2 heads, we will get the probability 1 by 4. Notice that getting one head has a likelihood of occurring twice, and head tail and tail head. This is your likelihood, and in this case, probability of y is equal to 1 is equal to 2 by 4. That means 1 by 2. This is your likelihood. Now, why are random variables important? And random variables generally produce some probability distribution based experimentation, some observation, or sometimes it will generate some processes also. And this random variable, there is need to understand some sample of the data, and by knowing the likelihood that specific value sometimes will occur in real world at some point in the future. Now, probability distribution for random variable. The probability distribution for a random variable describe how the probability are distributed over the values of the random variable. For a discrete random variable, we have said that X, the probability distribution, which is defined the probability mass function. And that probability mass function we will denoted by the f of x. And this function generally provide the probability for each value of the random variable. It will provide the probability for the each value which is available in the random variable, and in the development of the probability function for discrete random variable, there are two conditions. There will be always two conditions. First condition is your f of x should be non-negative every time. Your f of x should be non-negative every time for each value, and the sum of the probabilities for each value of the random variable must equal to 1. Now, in the continuous case, counterpart of the probability mass function is the probability density function. In discrete, it was containing probability mass function, but in continuous it is containing probability density function, and which is again denoted by the f of x only. And continuous random variable probability density function provides some height or value of the function for at any particular value of the x. That means it does not directly give some probability of the random variable on the specific value. So the area under the graph of the f of x, we can say the graph of f of x, which will corresponds to some interval. It totally depends on the interval, and we will get by computing the integral part of the f of x over the interval. So it will provide the probability that the variable will take on a value within that the interval. Now the probability density function also it satisfy two conditions. First, f of x must be non-negative for each value and integral over the value of random variable equal to 1. In this function, what was happened? There are also two conditions. What conditions? F of x should be non-negative and sum of the probability should be equal to 1. But in continuous, your f of x should be non-negative, but at the same time integral over all values should be equal to 1. Now expected value, or we can say mean of the random variable, is denoted by E of x, or we can say mu is a weighted average of the values the random variable may assume. And in discrete case, weights are given by the probability mass function, and in continuous case, the weights are given by probability density function. In discrete, weights are given by probability mass function, and in continuous case, it has given the probability density function. So formulas for the computing the expected values of the discrete and the continuous random variable are available. E of x is equal to summation of x into f of x. This is showing for the discrete. And E of x is equal to integration of x into f of x dx. This is showing for the continuous. And the variance of the random variable, it is denoted by the var of x, or we can say that sigma square, which is weighted average of the squared deviation from the mean. In discrete case, the weights are given by probability mass function, and in the continuous case, the weights are given by the probability density function. The formula for calculating the variances of the discrete continuous random variable are given as equation 4 and equation 5. Now, the standard variable generally is denoted by the sigma sign, and it is the positive square root of the variance. Since the standard deviation is measured in the same units as the random variable and the variance is measured in the squared units, the standard deviation is offered as the preferred measure. Now you can say that variance of x is equal to sigma square summation of x minus mu square into the f of x, or this is for the discrete and this is for the continuous. And variance of x is equal to sigma square is equal to summation of x minus mu square into f of x dx. Now, there are some special probability distributions. First one is the binomial distribution. Two of the most widely used discrete probability distribution are binomial and Poisson. And the binomial probability mass function provide the probability that X successes will occur in n trials of the binomial experiment. And this is your binomial distribution equation. F of x is equal to n of x into p power x 1 minus p power n minus x. This is your binomial probability mass function. Now, binomial experiment has four properties. First, it consists of some sequence of n identical trials. That means it will contain some n identical trials. Then it will contain two outcomes. Success or failures are possible on each trial. And the probability of success on any trial denoted P does not change from trial to trial. And the fourth one is the trials are independent. For instance, suppose that it is known that 10% of the owners of 2 years old automobiles have had a problems with their automobile's electrical system. Now, for to calculate the probability of finding exactly two owners that have had the electrical system problems out of the group of the 10 owners. Now you have to find out the binomial probability mass function used by setting n is equal to 10, x equal to 2, p equal to 0.1, and you have to put all these value in the equation 6. In equation 6, so you will get, after solving this problem, you will get the probability 0.1937. Now, the Poisson distribution. The Poisson probability distribution is often used as the model of number of arrivals at a facility within a given period of time. And for instance, the random variable can be defined number of telephone calls coming into the airline reservation system during the duration of the 15 minutes. And if the mean number of arrivals during the 15 minutes interval is known, the Poisson probability mass function is given in this equation 7, which is used for calculating the probability of x arrivals. Now, the formula is f of x is equal to mu of power x e to the power minus mu x naught. For example, suppose that mean number of calls arriving in 15-minute period is 10. So calculate the probability that 5 calls come in within the next 15 minutes. Mu is 10 and x is 5, and all these value you have to keep in the equation 7, and after solving the equation 7 you will get the value of 0.0378. Now we will see the normal distribution. The most widely used continuous probability distribution in statistics is the normal probability distribution. And the graph corresponding normal probability density function with mean mu is equal to 50 and standard deviation is here sigma 5. All normal distribution, and these things are shown in the figure, normal distribution figure. And all normal distribution graph, it is in the bell-shaped curve. And probability for the normal distribution can be calculated using the statistical table for standard normal probability distribution, which is generally normal probability distribution with the mean of the 0 and the standard deviation of the 1. Your mean will be 0 and standard deviation is 1. This is the normal distribution diagram. Whatever I have told, all things are denoted in the normal distribution diagram. And the sample mathematical formula is used for converting any value from normal probability distribution with the mean, which is denoted as mu, and the standard deviation, which is denoted as a sigma, into the corresponding value for standard normal distribution. And the tables for the standard normal distribution are used for computing the appropriate and specific probabilities for the events. And this is all about the collectively exhaustive events, normal distribution, some probability distribution, Poisson distribution, and these are some references so you can refer. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.